I'm gonna turn my screen on now. Hey Shannon, be back in 1 second here. Make sure I gotta turn this camera on and then we'll be good.
Still directing the audio.
But you hit the first one, then was that your second?
Yeah. I should have gone on the same place, but I was an idiot trying to get two. But I wasn't thinking.
Okay.
It was a tactical error.
I got you. Tactical.
Eyes in the moon.
There's 2 games started.
Wait, what?
Oh, it's the next
Yeah,
yeah.
How did I not hit anything? What the?
I'm good.
You want to talk about it? No, I don't want to talk about it. I'm disappointed.
Let's go.
I'm gonna just do a circle around this thing.
Oh, let's go.
Oh my god, you're hitting my things multiple
Now
times.
she
Like,
can make rolls, yes, just looking at it.
Yep, staring intently. Obviously, you want to learn so badly.
also. What? Okay, so it's that way.
Full problem.
Get somebody in there.
Oh.
Okay. Let me pass out to you guys. Yep. Alrighty. Okay, the lab that got recorded that was supposed to not be recorded, I changed from a score to complete incomplete. So if you have something with like complete scribbled, that's why. So like yours, I just changed to, it's just completed. There. Okay. You. Where did it go? Back here, I'll come back to you. Complete. There. You got one?
Hi, guy.
Oh. Hi, guy. Hi, guy. All right, let's see. More you. Okay, let's go, Alex. You. And Bailey. And I did that one for Abby. My name twice, just in case. I wasn't sure who. Yeah. All right, here we go. There you go. All right. So we live streamed our lab. It should be on the Facebook page already, and then I'll make sure it gets situated over to YouTube. There's Ivy. Make sure she gets in. Yes.
I have a brownie point.
Ah, okay.
For me, it says lesson 4 and I'll do lesson 5.
Yep. Yep, that'll happen. Good call. That's one of the hard things to catch when you're doing 4 copies of each lesson.
I think this might be supposed to say lesson 4, but it says lesson 3.
Yeah, that one was the other one. Somebody got that one. And the lab was off too. See, that's the crazy thing, because I use one as a template and I just keep building off of it, but I have to make 4 copies of each lesson because I do one for the juniors, one for me for the juniors, one for you, one for me for you. And somewhere along the way, I forget to change something in the formatting.
How many brownie points are there?
I think I'd have to look, but I think you guys are like around,
I know we're double digits.
I know, I was gonna say, I think you're around 15 or so. So you're doing well. All right.
Brownies are gonna come so fast.
So I've got a PowerPoint for today because some of this stuff was tricky to visualize, right? Well, why, he says. So who's in my chat saying hello? I let Ivy in. She's good. Okay, all right. You're good there? All right. Where's my screen share? Oh, there's Alex. Let me let her in. So I'm gonna go ahead and share the screen for you guys. You guys don't need to see that though. So I have a PowerPoint for y'all, which should hopefully make some of this a little more clear. Hey, you guys, can you keep it down? Can you tell them to keep it down? Thank you. Yeah, especially since there's like painters on the outside of the house making noise. We have this one spigot right out that window. And I don't know why, but when you turn that spigot on to get water, it goes, wah! So this morning I'm getting dressed and I hear this, wah! And then if you like, you know, pull the handle on the hose thing, it goes, wah, 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 wah. This is going to be all of class. Unfortunately, they have not turned it back on yet because that.
I'm confident it's the FBI thing to drill down.
Yeah, you know, it could be
I'm a pro conspiracy.
because 3 years ago, yes, I ordered snails for when I was teaching biology. Do you remember middle school biology? So I ordered these snails from this dude on Etsy, I think. No, Facebook, who sold snails. And I was so excited because we were studying invertebrates and these were big, they're big snails like this. And I thought, oh, this is great. Everybody can have a snail, you know, take it home or whatever. Well, after I ordered them and paid the guy, I realized that he was in Ukraine. And I thought he was just a guy with like a Russian sounding name who lived nearby, and he did not live nearby. So he lived in Ukraine. So I imported snails. I don't think that's legal. And I was panicked then because I didn't know what to do, but they arrived in a big box and all but 2 were alive. So yay, we did it. All right, so we're going to talk about atoms and moles and electron configuration and this whole mole thing. Did you see my shirt? Did everybody see it? Look, my shirt. It says 2 moles per liter. I like it. They're cute moles. I mean, 2 moles per liter. Yeah. So when you guys read about electron configuration, you were introduced to this concept of quantum numbers if you hadn't already known it. For whom is this totally new, this whole quantum number bit? Yeah, a couple of you? All right, so okay. So basically what you've got is there are various energy levels, right, within each atom. And then as we were saying in lab, you know, I think most people are familiar with Bohr models where you have the center and then, you know, ding, ding, ding all the way out. But in reality, it's way more complex than that. And they've done their best to kind of come up with the shapes of the various electron orbitals. It's not even the shape of the orbital. It's where you are most likely to find that electron. And it's within this given shape. But it's not that the orbital is that shape. So I'll show you as we go. So we talked about this earlier with the other group. So right here you guys have energy levels the way you've probably seen them before, right? And then here in your energy level 1, which they also call K, you've got what, 2 electrons, right? And then 8 and 18 and 32. And it kind of looks like consecutive rings, but if you're imagining it as 3D, maybe think of like an everlasting gobstopper, right? Where it's just like layers and layers and layers or shells around the center rather than 2D rings. But really, this is another example of a Bohr where they've got energy level 1, electron capacity 2, energy level 2, electron capacity 8, right? And you got your first shell, second shell. But in actuality, they get way more complicated. So the orbitals look, well, they say this is the shape of the orbital, but really it's not the shape of the path of the electron. As I said, it's the shape of the area in which you are most likely to find the electron. So if you're looking like, these would be your S orbitals, P's, D's are crazy shapes. You've got 2 different kinds of those. And then you get into these F and they get really complex. So I'm gonna try to see if I can give you a visual. See, that did not work. See if I can give you a visual to make it a little more clear for you. So we're gonna use, which element is this? Iron. Okay, we're gonna use iron. And this is a Bohr model for iron, right? So how many protons does iron have?
26.
26, all right. And so you would expect it to have how many electrons? 26. And if you look right here, sometimes on a periodic table, you'll see this. Do you see where it says 3D4S? Okay, this is telling you 3D6, 4S2. This is telling you where the very last electrons are placed. Cole, look at your dog on the table in front of Bailey.
No.
Right in front of the other camera. Oh, Lord. Okay. So this is the electron configuration for iron. The 1s2, 2s2, 2p6, 3s2, 3p6, and then the 3d6, 4s2. There it is right there again. See how they've done that for you? Now, I started with a different atom and it got confusing, more confusing. So I backed up and went with iron. So hopefully this little bit is correct on every slide. I went back and tried to fix it all. So you see that they've shared this with you. That gives you information if you're working on the periodic table. So let's say this is our nucleus, okay? There it says iron, all right? Remember that the shells were K, L, M starting at the middle. So if this is shell K, N would be energy level, right? So it's energy level 1. So this would be 1S2. So remember, S is like a sphere, right? So 1S2 would look like that, okay? So I've got the up and down arrows to show one of them's positive, one of them's negative. All right, so you have a sphere in your first level and you've got 2 electrons. That part's clear, right? Everybody understands that? And they're not in a circle, they're going around in the sphere. And if you were to look for them, you would most likely find both of them within that sphere. So when we move on to K, oh, that should say, see, I did it. KL, that should be L, see, I can't do it. I caught it, so it's not a brownie point. So here we go with N2, and you're gonna get your next sphere. All right, cool, this is making sense. And if you look over here on this corner, do you see right here where I have, first thing you're gonna fill is 1S, then you're gonna fill 2S, right? So here's 1S, that's what we did on the previous slide, and here's 2S. And how many are there? 2. So they're right there. One of those should be pointed up, see? I went over this like 15 times and I lost my mind trying to do it. So when you get to KLM, see, I gotta go back and fix that. It's gonna make me crazy. They start to look like this. So there's 1, 2, and there's a third one. So now you've got 1S, 2S, 2P. Okay, see here it is right here, 2P6.
There's a good chance that there's one thing in that area. So
Yes.
what's in the rest of the area?
Ah, did anybody look that up?
Extra credit about what's that?
Yeah, what is there where there's no electron?
See, my corporate Apple Spy
Mhm.
said anti-proton, but that's
Antiprotons, okay. Anybody else find anything?
Dark matter.
Huh?
Dark matter.
Dark matter. Did you find that? Or are you just guessing?
Found it.
Ah, so I'm like, what? Okay, hang on, we'll get back to it. All right, so the next shell up, we got M. And what do we have in M? Another S. So that would be this one right here, 3S. So we've done 1S2, 2S2, 2P6, 2, 2, 6. That gave us 2 in the first level, 8 in the second level, right? And now we're here. So it's another sphere, and that would be this guy right here. Now, I always think of S as a sphere. P, I mean, that shape is kind of like a dumbbell, they say. But if I thought dumbbell, I would think D, which is another level. So come up with something that works for P that makes you think of this weird shape that will help you remember what it is, okay?
Pedal.
A pedal, okay, yeah, they do kind of make like pedals, yeah. Okay, that's a good one, pedal. All right, so then what do you get next? Well, now we have our P6 again, and that would be this one, 3P6. So that's right, where is it? Right here, 3P. So we filled 1S, 2S, 2P, 3S, 3P. And now here come the next ones. And again, 2 electrons for each of these. And there's that. So now it's even funkier looking, right? You're wondering how they don't collide with each other. I'm wondering the same thing, except they repel each other. So they're being pushed everywhere because they repel each other, right? And then we get to our last shell, this N, and it's another S. And that would be this one right here, 4S2. So in the end, we have this big, crazy looking, oh, we have one more. We have 3D6. So if you look, these filled out of order, right? The way it's written versus the way it filled. Because you have to fill 4S before you fill 3D, right? Yeah. So we filled 4S as the sphere, and then we filled 3D with these things that are crazy kooky looking, right? Like these things looked like, if we go back to the slide that had them all, beep, 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 there it goes, it's disappearing. Whoop, whoop. One more. They look like these, right? It's like 4 things instead of 2 things, which is just so fun and confusing. So you can watch your atom grow. Ah! Awesome. And if you add them all up, you're going to end up with what? 26 electrons, right? And that's what we started with. And if you add them across the top, you also are going to get 26 electrons. Is that in the least bit clear, or is it still super confusing? A little bit of sense?
More.
We can watch it again. But you know what I need to do? I need to fix those that I labeled wrong, because I cannot label things right. So that's not K, that's L, right? And this one would be, see, it says L here, just not on that slide. Yeah, all right. Look at it again. Look at it again from here. Oopsie, I gotta move you because I can't push my button. There we go. So if we look at it again, you have your nucleus. Ta-da. We're gonna fill 1s2. That's the first one we have to fill over here, see? So if we fill it, it looks like that. That's this roughly the shape, and you got 2 electrons in it, right? The next one we have to fill is what, according to this?
2s2 or 2s.
2s, and we have 2 in 2s. The reason these have little superscripts because this is telling you how many are in this level. But sometimes if you have like smaller atoms, this one's not going to be finished. 2s2 is not going to get 2, it may get 1, right? So go into shell L. We have to fill the 2s2 in this case, and there's 2 in 2s. Except one of those is still upside down.
So 2s means second shell.
Yep. First sphere, second level petal.
Yeah.
But it's really the first one that looks like a petal. See, yeah, you have to kind of, like, remember when I said when you see this, you may want to write it in your own hand? That's why I said it. Yep. All right, so then you get into shell L and 2, and boom, boom, boom. Then the next one, there's your 3s2, 3p6. Now,
Why do you have to write 4s before
this
3D
one?
if 3D? Yeah, you said they're out of
So
order because
you
4s
write them in this order because, okay, this gets fun. All right. When you look, if you count up the number of electrons, it gets into the whole concept of valence electrons, which we haven't hit yet, but that's where it's, yeah, a little bit. Those are the ones that are in the outermost level that isn't, the ones in the outermost level, which oftentimes is not completely full, right? So they're the ones that are responsible for all the reactions and interactions because the other ones are all kind of locked into the structure. So it gets to that, but they fill, 4s will fill before 3. So this is energy level 1, energy level 2, energy level 3, but these 2 in 4 will fill before the last one in 3. I don't know why that happened. It's just the way that happens. But that's, yeah, So you just kind of have to know that once you get the 3 done, 3p, which would be right here, the next one's going to be 4s. So we were in a nice pattern until we got to this point, right? And then boom, there's your 4s, all out of order. And then you got to go back to your 3rd level and throw in these dudes here.
It's filled in a nice order, but it's not written in a nice order.
Yeah, if you filled all of 1, all of 2, all of 3, and all of 4, it would make more sense, but you're filling in part of 4 before you finish 3, and that's where it gets kind of funky. So for the purpose of like practicing and whatever, you absolutely should have this out. Like you should really be looking at this, and truthfully, as long as you understand this concept and what this means, I don't mind if you use this on your test, this thing right here. And there's one in your book, I'm pretty sure. But you can look them up, and it's just order of orbital filling. But you can absolutely use that if you need it, because memorizing that is difficult, what order they fill in, because it's not necessarily the order of the energy level, right? So anyway, like I said, you add them up, boom, 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 and you're going to get your 26. Add them across the top, you're going to get your 26. All right, so this is what we were talking about in lab, right? That when an electron moves up a level, it absorbs energy, goes from its ground state to its excited state. And when it falls down a level, it releases energy, and in lab we saw that energy as
Fire, flame.
light, colored light, but yes, light. So that's, now we were talking in the junior group about chemical bonds a little bit. We touched on it a little bit, and about whether forming a bond or breaking a bond is releasing energy versus absorbing energy. And we'll be getting into that too. So that's another way you have energy released and absorbed. And then this way, and what got them excited in lab? Why were they moving up?
The heat.
Yeah, from the heat from the fire and being burned. Oh, it's exciting. And then why were they falling back down?
Because they're cooling down.
Yeah, they were cooling down rapidly. And you just can't see it because there's so much at one time. So there's my t-shirt. 2 moles per liter, because I'm sorry, it's adorable. I like my little moles. They're so cute. There were lots of 2 moles per liter shirts. There were lots of these mole shirts, but I like this one best. I had to get myself a nerdy shirt. And I bought it just for today. I'm not kidding. Yeah.
Michael apparently loves the cheesy science puns. He thinks they're the funniest things in the world.
Thank you, Michael. I love the cheesy science puns too. I'll have to get a whole bunch of them for you because I know it's just what you want.
Yeah, next year just fill his binder with them. Send it to you.
Huh.
Just him.
Just randomly have a sign.
Speaking of things that are interesting and amusing, so Cole drove in the city.
I told the whole 2 of them.
Did you tell 2 of them? Well, hang on, wait up.
That's not classic.
Cole should share.
That's classical.
Just so that you know, real quick, for those of you who are missing class today, Cole drove for the first time in the city of Atlanta yesterday because we had to run an errand. Can you tell the story as appropriately as possible?
Yes,
Or shall I tell it for you?
Basically,
Speak up.
got at a stoplight and a naked woman on some drugs started walking towards the car and had to run the red light.
Yeah.
Kind of a awkward situation.
Yeah, it was pretty amazing.
Face just lit up.
No,
I mean, Kai, it was legit. Like, let me.
Where the guy just gets hit by the bus.
Yeah. So we're driving through 5 Points. Okay, we were going south down Peachtree Street. Okay, Kai's following me here. She knows where I am, right? And I said to him, once you cross over MLK, it can get a little sketchy sometimes, but what, we're all right. We were gonna go to Memorial, and instead of making weird turns, we just most direct route, which is kind of. So we had just passed the courthouse, and we're headed to the jail. And in between the courthouse and the jail, I said to him, "Oh, look out! Wait, there's a naked person in the street." And this person, I'm still not sure if it was woman or man, because had all of the clothing in front, and I couldn't really see. And person was like not with it, and walked right up to our car.
She gave me a Walking Dead zombie scare.
She did?
There. Like, that's how she looked at me. Exactly like in zombie from Walking
And
Dead.
I was like, Cole,
Like,
you're gonna have to go. So he runs the red light. So
Yeah, Cole is now a felon.
this is how you work with your permit. Apparently, you run red lights.
Yeah.
Back to our lesson. We were having a lesson. I know we were.
That's a job.
So what's a mole? Okay, here come my jokes. Hey, mole, where are you going?
Oh, no.
I have an identity issue. I need to find out who I am. What's a mole? This poor mole doesn't know who she is. Sad mole.
Focus on this. You love this. Michael loves you.
Michael loves my science puns. This is a cute mole. I'm sorry. That mole is adorable.
Yeah.
Do you know what this is called, by the way? This little thing that cartoons all carry? Okay.
Why do their noses look like pigs in a blanket?
I don't know. I had to look it up once.
Blanket you've been eating.
I had to look it up once because I was making a retirement cake for a guy who made bluebird houses, and she wanted a bluebird flying away. So I wanted the bluebird to have one of those little things that they always have in cartoons. It's called a bindle. I didn't know. So anyway, there's our little mole. So what's a mole? A mole is 6.02, or your book says 6.022
Yeah.
times 10 to the 23rd atoms. That's what's in a mole. And what element do they base it on?
12 grams of carbon.
They base it, yeah. Okay, so it's carbon that we're working with.
That's because it's
And-
solid. It's not because it's a solid and it's easy to
Well,
weigh and
It's
it-
easier to weigh, yeah.
easier to quantify.
Right. Did you see the part in your book about first we tried oxygen and that didn't work, and then chemists tried one thing and physicists tried something else, and everyone was confused, right? So here's a little summary. The mole is a counting unit. So counting units,
It's like a dozen.
yes, like a dozen. They call it the chemist dozen, right? So if you think of a mole like a counting unit, as opposed to something more complicated in your head, then it will make sense to you. So you abbreviate it without the E, which is just so helpful. You know, you've cut off one letter, it makes your life faster. So it's defined as the number equal to the number of carbon atoms in exactly 12 grams of pure carbon 12. So, oh, you're fine, Ella, come get what you need. Oh, stop it.
He's been here the whole time, man.
Awesome, leave it.
So chemists have decided, yes.
Ivy's in the
Place.
Ivy's in the waiting room again? Did we lose her again?
Yeah.
Thank you. Oh, well, that's weird. I admitted her. I lost her. I guess she came back. Maybe her internet booted her. How many of these Ivies are there? Admit them all. Okay. All right. So it has a value of 6.02 or 6.022 according to your book, times 10 to the 23rd. This is a number you will want to memorize and keep in your head forever. Amen. And when you're 43 years old and somebody says, hey, Jason, what's a mole? You just know it because it's still in your head. Yep. So what do we call that number? Avogadro's number, right? I've seen a lot of puns about avocado's number too. I'll send some of those your way, Michael. You know you like them. They're so fun. Avocado's number. And it's to honor Avogadro for all his contributions to chemistry. So 1 mole of anything is 6.02 times 10 to the 23rd units of that same thing. So you can count anything in moles. You got a dozen eggs is 12 eggs. A mole of eggs is 6.02 times 10 to the 23rd eggs. That's a lot of eggs. A what?
That's many eggs.
Many eggs. I can't even comprehend
That's
that
the
many
amount of
eggs.
eggs Gaston eats every morning.
10 to the
There you go. Gaston. So there you go. That one's for you too, Michael.
Michael, look at the memes. It's so funny.
No problem. Call
Look at it.
602-1023. There you go.
I wonder how much of,
Look at it.
how
Look
many
how
of us
awesome
are
it
going
is.
to try to call that number
It's
when we
so
get
funny.
home.
Just call me gold. Look at it. It's amazing.
Look at that mole. He has a hard hat on, a little miner's helmet, because you know they dig underground.
I really want to call that number down and see what happens.
And he has very thick glasses because why? Why do the moles all have glasses?
Because they can't see.
Yeah, they are blind. They live under the ground. Come on, people. All right, so here's some more about a mole. Look, it's a real mole. See? That's a real mole.
Okay.
There you go.
On the left or the right, I can't tell.
That would be Avogadro on the left. So what's a mole? Yes.
I found the brownie point.
Oh,
In the what's a mole? It had Avogadro with spelled Avogadro.
and this one here.
No, please.
One more back. I know. Hang on. That one?
Yes.
Oh, Avogadro. I didn't type this. I stole it from someone, and that person messed up, and I didn't catch it. Good catch. Avogadro's number.
Oh, good old Overgrado. I know him.
I like Avogadro. Yep.
Down on the south side.
So what's a mole? 1 mole is the amount of a substance that contains exactly 6.02214076 times 10 to the 23rd atoms, molecules, or ions. Atoms, molecules, or ions. So for example, some of the labs I have for you guys, it's going to say for me that I have to make a solution for you that is 2 mole hydrochloric acid solution.
Wow,
So that's obviously
that's a lot of hydrochloric.
going to, no, not necessarily. But that's going to be like 2 moles per liter is not that much, right? So that's going to be, in that case, molecules, right? Because we're talking about HCl molecule. And the number is also known as Avogadro's number, which we said. And there's a little NA, that's Avogadro's number, if you want to abbreviate it. And this dude is this Italian guy of Ovogredo, as they said on the last page. And it says here, which was a suggestion put forth by French scientist Jean Perrin to recognize Avogadro's work. So they're like, hey, this important number, let's give it to this dude. Right, exactly. And there's a real mole. And if you have tunnels in your yard, it's probably voles, not moles. Moles are much bigger. They're big, like big. The little tiny ones are voles or shrews. All right, so here, look. 1 mole is essentially, and there's the number, and I'm not reading it, of something in chemistry. It's billion of something. So of water, it's about 18 grams. Of iron, it's about 55.9 grams. Oxygen's about 32.0. Sodium chloride is about 58.4 grams. Gold is about 9. Is that a period? 197. I couldn't tell if there was a decimal in there or no. And then helium is about 4.
And carbon is 12.
Yes. So 1 mole is a different mass for different elements and compounds. This may seem confusing, however, it's similar to comparing a dozen elephants to a dozen mice. Although their masses may be different, you still have a dozen of each. So obviously, helium here is 4, right? Somebody tell me what's, the biggest one here was gold. Somebody tell me what's gold's number.
Gold's number?
What's its mass?
I said 197 grams.
No, is it that? Yes, a mole of gold. I'm wondering what's its mass.
Oh, it's mass number?
Uh-huh.
Oh.
Oh, I have a theory.
Should be in here. Ah, he's got it. 196.9.
6, 7.
So, yeah. Now think about that. Hold on here. Looky here. Look at that. 197. Somebody tell me what's iron. What's the mass for iron?
55.845.
55.845. See, it says 55.9. Okay. And then what was helium?
Helium's 2. Or no, it's 4.
The mass is 4.
4.003.
All right. So then water.
So a
How do you get water?
Hydrogen, 2 hydrogen, and 1 oxygen.
Yes. So
What's carbon?
2 hydrogens are 1
I know.
and 1,
Yeah,
right? And then what's the oxygen?
15, so it's around
15. Yeah, 15 point, well, what is it? It's 15.99. So 16 plus
And
1 hydrogen and 1 hydrogen is going to give us,
17.7 or 17.
and what do we have?
I can't
18. There you go. And then look at that one, sodium chloride. What's sodium and what's chloride? What's the mass number for sodium?
It's. Oh,
Chlorine is 35.453.
35.4. Uh-huh. And what's sodium?
Sodium is 22.9.
23 roughly. And if you stick those together, do you get 58.4? What do you know?
Wow,
Isn't that cool?
it's almost like they thought that through.
I know, it's almost like they did. Okay, so a mole is often referred to as a chemist's dozen. It's just sorry. It's just an easier way to count large numbers of atoms and molecules. The number of moles equals your mass in grams divided by your mass of 1 mole. So here we'll make sense of that. All right. Hopefully there's sound. There was last time. Nope.
Welcome to Multi-Conversions Made
There we
Easy, brought to you by Ketchbook. In this video, we're going to learn how to do mole conversions for elements, how to calculate the molar mass of a compound, and how to do mole conversions for compounds. But before we jump into all that, you might be wondering, what is a mole? Well, there are lots of different moles in the world, but in chemistry, a mole is simply a large number of things. It's kind of like a dozen, only bigger.
Cute mole.
1 dozen is 12 things. 1 mole is 6 times 10 to the 23rd things. That is 600 billion trillion things. Now that's a lot of things. But why is the mole such a big number? Because atoms are so small. Suppose you wanted to know how many hydrogen atoms are in 1 cup of water. If you were able to count all the atoms, you would find that there are about 15 trillion hydrogen atoms in a cup of water. But if we count using moles instead, that works out to be only 25 moles of hydrogen atoms. So we use moles to count atoms, molecules, and other chemicals. It turns out that there is an even better reason why 1 mole equals 6 times 10 to the 23rd things. And that is that 1 gram equals 6 times 10 to the 23rd atomic mass units. Let's see what that means for a particular element. Break out your periodic table and look for lithium. It's the 3rd element. On the bottom of the square, you should see the number 6.94. This is the atomic weight of lithium, but it is also the molar mass of lithium. So 1 lithium atom has an average mass of 6.94 AMU, and 1 mole of lithium atoms has a mass of 6.94 grams. That gives us a convenient way to count atoms by weighing them, and the molar mass is the conversion factor between grams and moles. Let's try a problem. How many moles of lithium are in 25 grams of lithium? This is a one-step unit conversion problem, and like any unit conversion problem, the first thing you should do is write down the quantity that you know. In this case, 25 grams of lithium. Next, multiply this by conversion factor fraction. Remember that for mole conversions, the molar mass is always our conversion factor. 1 mole of lithium equals 6.94 grams. Because we started with grams, we put 6.94 grams on the bottom of the fraction. Grams on the top and bottom cancel each other out. Next, write 1 mole on the top of the fraction. Because the 1 is on the top of the fraction, this becomes a division problem. In your calculator, type 25 divided by 6.94. The answer is 3.6 moles of lithium. You may have been wondering, what happened to the E in mole? Well, it turns out that the abbreviation of mole is MOL. Isn't it just wonderful how much energy we're all going to save by not writing the E?
Right?
Okay, time for another sample problem. What is the mass of 11.5 moles of lithium? Before we solve this problem, we realized that mass is measured in grams, so we need to convert from moles to grams. The first thing you should do is write down the quantity you know, 11.5 moles of lithium. Next, multiply this by conversion factor fraction. The molar mass of lithium is still the conversion factor. Because we're starting with moles, 1 mole goes on the bottom and 6.94 grams goes on the top. Moles in the top and bottom cancel each other out. Because 1 is on the bottom of the fraction, in your calculator type 11.5 times 6.94. The answer works out to be 79.8 grams of lithium. That is how to convert between moles and grams for elements, but what about molecules and compounds? Let's start by looking at molecules made from carbon, nitrogen, and oxygen. The molar mass of each element is typically written on the bottom. Now, in order to convert between grams and moles for a molecule, we will need to calculate the molar mass of the molecule by adding up the molar masses of all the atoms in the molecule. Let's try a few examples. Carbon monoxide has 1 carbon and 1 oxygen, so we add 12.01 for carbon and 16 for oxygen to get a molar mass of 28.01 grams per mole. In general, the units of molar mass are grams per mole. However, it is very useful to write the molar mass as an equality. 1 mole of carbon monoxide has a mass of 28.01 grams. That helps us remember that the molar mass is a conversion factor. Let's try another molecule. Nitrogen is a diatomic element composed of N2 molecules. Because there are 2 nitrogen atoms per molecule, we multiply 14.01 by 2, so the molar mass of N2 is 28.02 grams per mole. For carbon dioxide, there is 1 carbon and 2 oxygen atoms. So we add 12.01 for carbon and 16 times 2 for the 2 oxygens, which gives us a molar mass of 44.01 grams per mole. We can do the same thing for ionic compounds, like magnesium nitrate. The molar mass of magnesium is 24.3. Because there are 2 nitrates in the formula, that means we have 2 nitrogen atoms and 6 oxygen atoms. So we add 24.3 plus 14.01 times 2 plus 16 times 6, which works out to be a molar mass of 148.3 grams per mole. Remember that we can write the molar mass as an equality. So for magnesium nitrate, 1 mole equals 148.3 grams. That is our conversion factor between grams and moles. So let's go ahead and use this molar mass to do some mole conversion problems. Let's convert 6.35 grams of magnesium nitrate to moles. We will solve this problem in exactly the same way that we converted grams of lithium to moles of lithium. First, write down the quantity that we know, 6.35 grams of magnesium nitrate. Next, multiply this by a conversion factor fraction. The molar mass of magnesium nitrate is our conversion factor. Because we started with grams, write 148.3 grams on the bottom. Because we are solving for moles, write 1 mole on the top. grams on the top and bottom cancel out. Because the 1 is on the top, and your calculator types 6.35 divided by 148.3. This works out to be 0.0428 moles of magnesium nitrate. What if we wanted to know the mass of 0.369 moles of magnesium nitrate? First, write down the quantity that we know, 0.369 moles of magnesium nitrate. Next, multiply this by a conversion factor fraction, using the molar mass as the conversion factor. Because we are starting with moles, put 1 mole on the bottom. And because we are solving for mass, put 148.3 grams on the top. Moles on the top and bottom cancel each other out. Because the 1 is on the bottom of the fraction, multiply 0.369 times 148.3, which gives us 54.7 grams of magnesium nitrate. Thanks for watching. If this video helped you at all, please give me a thumbs up. It means a lot to me. Feel free to also share any comments or questions you have below. Subscribe to my channel.
I like that. I like the Doodly. What is it? Doodly, is that the app that lets you do that? And there's a couple others. I like that. All right.
Or
So
check me out
no.
at petsbook.com.
I don't want to check you out. Thank you. Did that make sense? It's just conversion factors like we did before for metric units, except this time we're going to use that AMU number at the bottom for atomic mass, and that's going to get us what we need for our conversion factor. So in your notes, pull your notes out, and let's go over these and see how y'all did.
I totally finished my notes.
Good. You're also going to grab them if you don't already have them.
I got all the letter ones, but the ones I actually had to write down.
Some of these were hard. Some of these weren't so hard, and some of these were like, tricky. All right. Michael's gone. Okay, so who has an answer for number 1?
D.
D. All right. Avogadro's number is the number of atoms or molecules in 1 mole, equal to 6.02 times 10 to the 23rd.
Yep.
And what do we get for number 2?
A.
That's right. A, atomic mass. The mass of an atom expressed in atomic mass units. Hang on, anything important over here? No, we're good. All right. And what do we get for 3?
B.
We got B. So a mole is the SI base unit to measure the amount of a substance whose number of particles is the same as the number of atoms in 12 grams of carbon-12. And then lastly, we got C, right? Your molar mass is the mass in grams of 1 mole of a substance. Do you have your notes, Ethan, or you not have them?
Me and Abby did them together.
Okay, cool. Got the same answers. All right, so who would like to help me with number 5? Which isotope defines the atomic mass unit, and how is the atomic mass unit defined?
Abby really wants to.
Abby really wants to answer it. Abby really wants to answer it.
Oxygen and atomic mass is defined as atomic masses expressed. What did you write?
I don't know. You copied it. So,
You read this, you wrote it.
I bet. Give it to me. Oxygen and atomic mass are defined as atomic masses expressed as the ratio of the mass or an atom to the mass of a hydrogen. I don't know what I wrote either.
Does anybody have something different? What do you have?
Wait, hold on.
Carbon 12 is the isotope.
Carbon
that defines
12.
a mole just because it's easier to weigh because it's a solid as opposed to maybe
Yeah.
a certain set.
So it's carbon 12 we're looking for, yeah. And it's because, like you just said, it's a solid. There were other reasons too. Did you see what they were in your book? They mentioned some other stuff about how it, where's that? Do you have your book? Oh, no, mine's right there. There were a couple of things they listed.
You can jump through.
I know, I was like,
Remember what we did on Friday?
They talked about how it was a solid, yes, but there was something else. What was it? I wanted to read exactly how they put it. They said, atomic mass unit has been defined in a number of different ways over the years, right? And it says, originally atomic mass expressed ratio of mass as in mass of an atom to a hydrogen atom. Using hydrogen as a standout turned to be inconvenient because hydrogen does not react with many elements. So then they moved on to oxygen. Cole. They moved on to oxygen, and it said oxygen combines with almost all other elements, but so oxygen became a standard, right? But then it says the atomic mass of oxygen was defined as exactly 16, and the atomic mass of other reactants were based on that standard. But that choice led to difficulties because oxygen has 3 isotopes. Physicists based their masses on the assignment of 16.0000 as the mass of the most common oxygen isotope, but chemists, on the other hand, decided that 16.0000 should be the average mass of all oxygen isotopes. So then, to a physicist, the atomic mass of fluorine was 19.0044, but to a chemist, it was 18.9991. So that's going to cause issues. So then they all finally agreed. When did they agree? 1962, not that long ago. They agreed to use carbon.
How are we just so nice as people with the degrees?
It says they agreed based on an isotope of carbon. Carbon, yes, it's exactly 1/12 the mass of carbon 12.
I know.
Right.
Like,
That's the hose I told you about.
Isn't that what the pressure washer?
I don't even know. We'll have to ignore the sad moaning of my house. So why is a mole used to it is, it's moaning, isn't it? Like the house is sad, it's crying. Why is a mole used to count atoms?
Because instead of counting atoms in an element, moles make it easier because they're predefined in value.
Okay, what do you have?
most samples of elements have a lot of atoms, so they just made it easier to work with.
What do you have, Michael? Anything else?
Just atoms are so tiny, there's so many. So you need
Yeah, that's exactly what I've got. They're so small and there's so many of them. We needed something easier to count with. All right. So
It's there
Yeah.
because they're the
what's the relationship between an atom's atomic mass and 1 mole of that atom? Cole, you got it?
Yeah, this one in particular I took from the book, but the mass in grams of 1 mole of an element is numerically equal to the element's
Right.
atomic mass
Yeah.
periodic table.
Right, so they're the same. Atomic mass and molar mass are the same, which is why we can use it as a conversion factor.
Right. And I was also right on this one, Abby. So.
Oh, they're fighting over it. I love it.
Yes, I said that. I said you're so
You're missing the fight.
Yeah,
Look,
because I said
you're like-
that yeah, exactly.
Don't
That's what you-
cheat.
Guy, wake up!
Kai, wake up.
Acrimony team.
Kai looks too comfortable. All right, so how about number 8? The atomic mass, Cole, he's fine then. The atomic mass of lithium is 6.939 AMU. Would you expect the isotopes 6,3 lithium and 7,3 lithium to be equally common? Why or why not? And if not, which isotope would you expect to be more common? Who has an answer for that one?
You do that one.
Abby has it again. All right, Abby.
I answered this one. So.
She answered this one. What you got?
I said I would expect
Ethan?
7,3 lithium to be more common because the atomic mass is equal to.
There you go. Abby is on the right track. Yes. Your 7,3 is going to be more common because, oh, that's a typo. There should be 6,903. Anyway, it's closer to 7. See, I can't type the lithium 6,939. What? Look at that. Hang on. I got to fix
7-3
it.
is more common.
I got a different answer.
Okay, okay.
Well, not
7-3 is more common.
Yeah. It's
It is.
Greater natural abundance.
Yep.
Go deep.
Hold on. Don't look at the other answers.
Man, you're so smart.
There you go. All right, what is the mass in AMU of 1 fluorine atom?
Is that 18.9? Yeah.
18.99 AMU, right? And how'd you get that?
You added
Nope.
the.
I don't remember exactly how I got it.
No, that's an easy one.
Yeah, you added
You don't
the-
remember because you didn't have to do anything to it.
Right, yeah.
You found the answer looking right at the periodic
Bottom of the
table,
periodic
right?
table.
That's why you don't have anything there, because that's where you got it. You just wrote it down. And here it is right here, look, 18.998. See it?
Yep.
All right, what's the mass in grams of 1 fluorine atom? Did anybody get an answer?
I got
Oh,
it.
here it's 3.16 moles.
Okay.
Or no, it's half.
16.
So what you do is you're going to divide the molar mass, right, by 10 to the, that's supposed to say 23rd, but I
Yeah.
copied it and it didn't give me a superscript, atoms. When you divide it, I got 8.15 times 10 to the 23rd. What did you get?
I got 3.16.
Okay.
We have 3.16.
Do you have 3.16? Wait a minute. I may have done this one.
Yeah.
Oh, wait. You guys have the right one. Hang on.
That's good.
All right. Wait a minute.
Does that count as a brownie point?
But sometimes that's going to happen. Let me see. Let me make that one a superscript first. Because that's screwy. This was one of the ones I did last night. Okay. What'd you get, Michael? I may have just
3.16 to the times 10 to the
tried the
negative 20.
movement. Oh, that's fun. All right. I'm going to come back and look at that one because I think what? Look at that. I think when I copied it over, it got weird on me. All right. We'll come back to that one. So what did you get for the next one?
6.0.
Yeah, isn't that just 6.022?
That's right. Yeah. Okay. We'll come back to that
But
one.
it says 16 point.
It sure does. Gosh, you know why? Because these are the ones that last night I was trying to whip through and put my computer away. There we go.
That's brownie point.
Yeah, that one is. All right. So then, yes, obviously, how many molecules are in 1 mole?
Yeah.
All right, of carbon dioxide. But what is the mass of 1 mole of carbon dioxide?
12 grams. That's 12
Yeah.
grams.
12 grams.
12 grams.
No. So you have, here is your mass. Here's your carbon, right? And it's 12
CO2, my bad.
CO2, right? So you have your O,
Yeah, so
And then 2
12
O's.
grams, yeah. times
Right.
2, okay, yeah, 40.
right? 44.01. Do you see how we got this? So here's your oxygen. It's 15.99. You're going to double that, and you're going to add it to the carbon dioxide.
Yeah, 40.
All right, there you go. Are you over there working that other one, Jason? Is that what you're doing?
Yeah, I just thought it was the atomic number itself.
Oh.
Are you doing 1 atom?
It was, let me go back and look.
Mass in grams of 1 chlorine atom.
Yeah, the mass in grams of 1 fluorine atom, your fluorine is 18.99 AMU. So if you're using the conversion factor of grams per mole, it's 18.99 grams per mole. So where did we, I'll scooch that over. Oh, we'll come back to this one. All right, I'm gonna come back to that one. Because I pulled that off of one of the resources and stuck it in, so something's up. Complete each statement below by writing the correct word in the
Well, it's going to
space.
be very, 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 very small.
Yeah, exactly. So this, yeah.
That's it.
So Alexa, what is 18.99 divided by 50? Oh, sorry, Alexa, cancel. Alexa, what is 18.99 divided by 6.02 times 10 to the 23rd?
18.99 divided by 6.02 times 10 to the power of 23 is 315.4 billion trillion.
Thank you, corporate Amazon
Million
spy.
314.4 times 10 to the 23rd.
One of my favorite memes ever, 1980. Oh no, this line could be wiretap, 2020. Hey, wiretap.
Yeah, exactly. All right, so all electromagnetic radiation, including visible light, can be thought of as moving what? Moving what?
Waves.
Waves.
Mhm.
Or, right, waves and particles. There we go. Waves and particles. As the frequency of a wave increases, what happens to its wavelength? Very good. Decreases, shortens. Yeah, we did learn that last year, right? And that was in the lab today. Remember I showed you low frequency on one end? All right, to define the region in which electrons can be found, scientists have assigned 4 what? Quantum numbers to each electron. Very good.
Do you want me to just read off the order?
No, we'll go through them. All right, so what did we get for electromagnetic spectrum? Where did my people go? Hold on.
I did, Jade.
Where did my faces? I lost my people here. You guys still seeing me? Seeing my screen? Or did you lose my screen? Suddenly your faces disappeared for me, so, and I didn't hide them, so I don't know where they went.
Open up. Do you want to see them or do you?
No, it's okay. It's just if they're waving at me, I can't tell. All right. So what do we get for electromagnetic spectrum? J. All of the frequencies or wavelength of the electromagnetic radiation. Can we see all of it? No.
Electromagnet?
Do we see most of it? No, we see only a tiny, tiny, tiny portion, right in the middle, right? Visible light, right smack in the middle.
What's the animal? There was one animal that sees almost all of it, right?
Yeah, we did
Yeah, I can't remember.
talk
what it was.
about that. What
Yeah.
was it?
It's like I think a dog sees more of it or less of it.
They see it in a different range
Yeah.
than we do, and that
There's one
has to
animal
do
that
with.
sees a lot of it.
Yeah, I can't remember. It was
Animal.
He's like a cat.
No, is it a bird?
maybe
A
the
bird might make sense because it.
maybe the spy knows.
Can't they see?
We could ask her. Hey Alexa, what animal sees the most of the electromagnetic spectrum?
Here's something I found on the web. According to wiseandcheap.com, birds can actually see more of the electromagnetic spectrum than we can. In many colors, which we can never see.
Just can't they see?
It probably helps
Very
with.
cool. I know,
finding prey.
Yeah, and I know insects can too. Like, have you ever seen the pictures of flowers from a bee's
Yeah.
point of view? Very different.
That's why I
Yeah.
don't want to wear yellow outside. Already bright colors.
So how about electron configuration? What did you guys get for that one?
C. E. Sorry.
E, the arrangement of electrons in an atom. And how about excited state?
See.
Woo! Yeah, it's excited state. I'm sorry, that always makes me laugh. The state in which an atom has more energy than it does at its ground state. Ground state is just boring. All right, how about ground state?
G.
Here you go. Your lowest energy state of a quantized system. Hund's rule.
Is that I?
What do we have?
I.
L states that for an atom in a ground state, the number of unpaired electrons is the maximum possible, and these unpaired electrons have the same spin. Yeah, I know. There's that one, and then there's off bow and poly, and they're all, yeah. So a line emission spectrum. Yeah, now this is what we were talking about in lab when I said, if you look at any of these atoms doing spectrometry, you'll see all those, yeah, the lines. And there were pictures, weren't there? Didn't you guys have pictures? I thought you guys had pictures of the line emission spectrum, didn't you?
There might have been one in the.
I know I saw some this week, but I was also putting together the slideshow, so I very well may have seen them. I'll look one up for you in a bit. What do you get for orbital?
Orbital is F.
F. Okay, there we go. A region in an atom where there is a high probability of finding the electron. So like I was saying, it's not the shape of it so much as it is the region where you're likely to find it. Oh, I did that early. G. Pauli exclusion principle states that two particles of a certain class cannot be in the exact same energy state. Blah, 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 blah. How about number 9? What do we get for number 9? D. Ooh, I did that one early. Look at that. Okay, photoelectric effect. Oh, I know why, because I had to go back and do one of these. So what occurs when light strikes metal? We talked about that in earth science, I believe, as one of the ways they can identify metals.
Yeah.
So there's D. Yeah, quantum number is D. Number that specifies the properties of electrons in an atom. Quantum theory. Yep. Present day model of an atom in which electrons are located in orbitals. And the last one, off-bow principle, states that the structure of each successive element is obtained by adding one proton to the nucleus of the atom and one electron to the lowest energy orbital. These are wordy things. I don't like definitions that are wordy like that. I rewrite them when I get the opportunity. All right, so let's look at this one that caused us an issue. Let's put up the whiteboard if I can get it to go. All right, whiteboard. All right, somebody who has the problem visible, because I have now the whiteboard visible. Let's see what we have.
You just want number 10? Is that what you're asking?
Whichever one that was, what was that?
So what
Yeah.
is the mass in grams of one fluorine atom?
Mass, I'm gonna eject this if it'll let me. Will it let me if I'm live streaming? Come on, do your thing. Yep. Okay, mass. It doesn't ever let me erase either. That makes me crazy. I actually have an eraser that I'm used to using, but it doesn't work in Zoom.
Yeah.
Yeah, it's annoying. Okay, mass.
Zoom detects
Come on.
a mouse, not a.
Yep.
There we go.
Mass in grams Of what? 1 gram of one what?
1 fluorine atom.
Of 1 fluorine
Was it fluorine or
atom. Fluorine. Okay.
Is it like
So what do we know? What do we know? Remember, we need to find what we know and what we don't know.
okay, so wait, periodic table, fluorine.
Mm-hmm.
Was that, what is that, FL?
Ugh.
FL?
Yeah. It's F. I went F. I don't know why. I know better. I know that one. Okay, so what is the mass?
I don't know, I am.
No.
Oh, it's 18.998.
18.998 what?
AMU.
Atomic mass units. All right, now we know that. So let's put it here. 18.998 AMU is what we know. Okay, so that means where do we have to put AMU?
On the bottom.
On the bottom, and it needs to be
Over 1 mole. Above.
we want to know grams, right? So we're gonna have to have grams on top. So what has grams on top? Mole, come on.
Wait, isn't
No,
that
no, no.
conversion supposed to be for
Hold on.
moles to grams, not AMU to grams or AMU to moles?
Okay, so we want to know the mass in grams, right? But what do we know? An AMU is equal to what?
1 gram of the mole.
Right, 1 gram. Okay, yeah.
AMU is equal to what?
1 gram.
Of the mole.
No.
No, not 1 gram.
1 gram of the mole, 1 mole of the gram.
It's how many grams are in that mole. Right?
How many grams are in that
You guys
mole?
remember because if carbon is 12, it means there's 12 grams of carbon in that mole, which is why.
Don't worry about carbon 12.
I'm using it as a.
Where's the one? I'm looking for the one that has it in it for you.
In that mole, it's not 1 gram, it's 1 mole.
Trying to find the one that had it.
It was toward the beginning.
This guy had it, I know.
Yeah, 348.
Remember when he said,
148.3
I want you to tell me. 148.3 what?
grams.
Grams? That's your answer?
Welcome to Mole Conversions
Hold on.
Made Easy, brought to you
Where
by
is,
Textbook.
stop,
In this video, we're going to learn how to do mole conversions for.
I'm trying to find the part where he talks about, right here. Here we go, let's look again.
We'll look for lithium. It's the 3rd element. On the bottom of the square, you should see the number 6.94. This is the atomic weight of lithium, but it is also the molar mass of lithium. So 1 lithium atom has an average mass of 6.94 AMU, and 1 mole of lithium atoms has a mass of 6.94 grams. That gives us a convenient way to count atoms by weighing them, and the molar mass is the conversion factor between grams and moles. Let's try a problem. How many moles of lithium are in 25 grams of lithium? This is a 1-step unit conversion problem, and like any unit conversion problem, the first thing you should do is write down the quantity that you know. In this case, 25 grams of lithium. Next, multiply this by a conversion factor fraction. Remember that for mole conversions, the molar mass is always our conversion factor. 1 mole of lithium equals 6.94 grams. Because we started with grams, we put 6.94 grams on the bottom.
Okay, so.
Suppose you wanted to know how many hydrogen cup of water.
Stop.
If you were able to count
He does
all the
not
atoms,
stop.
you'd find
Look.
that there are about 50. No, that's a lot.
I don't have
of
space on
things.
this.
Why is the mole such a big
I gotta
number?
pull up this
Because
and it becomes a
atoms are
thing.
so small. Large number of things.
See, that doesn't, there. It's faster if you can usually click, but, all right, where did my whiteboard go? All right, so what did we determine?
That 18.99 AMU
Is equal to what?
is equal to 18.99 grams in a mole, right? Or grams. It was like moles equals, the molar mass equals that.
Mole, this is also the molar mass, correct.
I know you showed me this before.
Who has a suggestion for what we're gonna put in here for our conversion factor? We want AMU on the bottom,
Yeah.
right? And we want grams on the top. We know this, right? Okay, so what do we need? How do grams relate to AMU? What did dude just say here in this long video?
Well, he said
Look right here. 1 mole is equal to,
148. I can't.
yeah. Can I? Yeah, that says 143. Oh gosh, I hate that there's no eraser. Good. That's gonna make me crazy. I'm gonna lose my mind over that. So how does a gram relate to AMU? So look back here. He just said it.
148.
He said they were equal.
He said they were equal,
Yeah.
right? So they're
Welcome to
equal. So
Molten
oh
Versions.
shush.
AEU, brought to you by
This dude
Kettle.
again.
In this video, we're going to learn how to do mole
He
conversions.
said they're
for
equal.
elements.
So if they're equal,
How to calculate the mole.
stop. Okay. So if they're equal, then
18.998 AMU.
18.99 AMU.
Below 18.998. Is it even help?
No. let me hang on. All right. Then you just get 1, right? Yeah.
You look like you're talking about.
Welcome
Hold
to
on.
Mole Conversions Made Easy, brought to
This guy's gonna make me nutty.
I'm definitely not subscribing to you now.
Yeah, really. Mhm.
Welcome to Mole Conversions Made
Fast
Welcome to
forward.
Mole Conversions Made Easy, brought to you by
Fast
Kettle.
forward.
In this
Oh.
video, we're going to learn how to find that there are
Okay, right here.
any conversion problem. The first thing you should do is write down the quantity that you know.
All right.
In this case, 25 grams of lithium. Next, multiply this by
Okay, freeze him here. It keeps going back to the first screen. I'm trying to get him to freeze on that screen, but it's not doing it for me.
No, it's gonna go back to the thumbnail.
Yes, I know, and it's annoying.
You want me to look at the video on my phone?
No,
Welcome to Mole
I
Conversions.
know.
Lots of different moles.
I'm gonna
in the
move him
world,
along,
but in
though. Here.
chemistry, a mole is simply a large number of things. It's kind of like a dozen.
I'm having a day.
Wait, I'm on.
10 to
What?
the 23rd thing.
Okay, here we go. No, right here is where I wanted to go. Hang on, wait.
Top of the fraction, this
All right, there. There we go. Okay,
That's mole to gram, not AMU to gram.
AMU to gram, mole to gram. So this one is 1 mole of something. Now, our problem asked, where's our problem? Mass in grams of 1 fluorine atom. Okay, we don't know the grams, we want the grams, right? But what do we know about the atom that we can use? We know the AMU. Okay, so is this, first off, is this going to be a big number or a little number?
It's little.
It's going to be little, right? Very, very, very little. Because you're talking about grams of an atom.
Is this the negative 20? Yes, it was.
3.16 times 10 to the negative 23.
3.16 times 10 to the negative 23rd. And how did you get it?
I get it on Wednesday, so I
No, I'm pretty sure that's right. So I think mine was obviously something wrong in the stuff. So how did you get, well, I didn't do that. How did you get,
I didn't know, I don't remember.
you don't remember how you did it? Do you remember how you did it?
I didn't write down.
You didn't write down. Okay, but we got it.
Um,
So who are my math people? Alex is a math person. Michael is a math person. How do we get this?
I think it's, you divided the 18.998 by Avogadro's number
Which goes where?
on the bottom.
On the bottom. Okay, so if Avogadro's number is going on the bottom, how are we going to make that into a conversion factor?
By putting 1 gram on top.
1 gram of a substance is what? We put 1 gram up there, and then we put down here 6.022 times 10 to the 23rd. Okay, so Alexa, what is 18.998 divided by 6.022 times 10 to the 23rd?
The answer is 3.15477 times 10 to the 23. Did that answer your
3.154,
question?
so it rounds down to 3.1.
Mm-hmm. Yes.
Also.
So what's with the,
The negative.
so wait a minute here, what's our,
That what Alexa is doing is, it's dividing by 6.022 and then multiplying by 10 to the power of 23. Not multiplying divided by 6.022 times. 10 to the
right. So we have, you have it good. Helps if I actually make room for this. There you go. All right. So back to that. All right, let me put this back over here. Okay. So you guys have, let's see, I'm no longer screen sharing. Let me take it off here. So we are about to wrap up Unit 2. I mean, yep, so that, what does that mean for you guys? What's coming today if we've wrapped up a chapter? You have a test. Okay, so here's what I want you to do. You can get out a pen and paper and write notes, or you can come back and look at this later, but I'm gonna tell you what to study. Okie dokie. Chapter 3 test is due next week. Not screen sharing. All right. Okay, good. Because I'm not screen sharing. All right. So, so you're going to need to know what you call atoms of the same element that have a different mass and why they have a different mass. There you go. You're going to need to know which subatomic particles have the highest mass. And you're going to need to know the definition of ground state. You're going to need to know which subatomic particles have the least mass. You're going to need to understand Avogadro's number in terms of a true or false question regarding its definition. So really understand it. And then, let's see. You're going to get a multiple choice question about definition of a mole. So you'll pick the best definition. Oh my gosh, is that NFL music playing on your phone?
That was actually Fox News and it was about the NFL.
Da-da-da, da-da-da. You're so funny.
I turned all my notifications on because football's on Thursday.
All right.
Thursday.
So then,
Chiefs, Texans.
gonna need to go. Gonna need to know how many electrons are present in an atom of a particular element if it has a certain atomic mass and a certain atomic number. Mass number, sorry. Atomic number and a certain mass number.
It's atomic mass.
I'm going to give you its atomic number and I'm going to give you its mass number, and you're going to tell me how many electrons it has.
It's mass number minus atomic mass.
You'll figure it out. Remember, we're doing electrons, right? All right, and then you're going to need to determine stable electrons and orbitals and how many electrons they can have and be stable. Like, what's kind of the max number of electrons in an orbital? In an orbital, not an energy level. Think about the difference. When we put all those orbitals up there, how many electrons were in each one of them? Do you remember how many were in each one of them? Two in each one of them, that's right. There weren't more than two. And you're gonna have a word problem about a certain amount of grams of an element. And then you're going to need to know how many atoms are in those grams. That's okay. It's a word problem that's going to say there's a certain amount of a substance, and it's going to give you its mass, and then it's going to ask how many atoms are in it. Okay? Yeah. Yep. And I'll try to find a couple other videos to put in this week's email that have even more. Here's another way. Look at it this way. Look at it that way. Look at it this way. Now, we talked about, that's it too. It's 12 total points. It's 1, 2, 3, 4, 5 multiple choice, 3 true or false, and 1 short answer. Okay. Now, we talked about how, let me go back and open my screen up again for them, about what in the world is in the space, right? Did anybody look that up and find answers? What's in the space between the particles of an atom? Oh, I have this cute picture up here too. I gotta show you. Let me get this up first. Hang on. Connect. Do your thing. I have an adorable picture up. This is actually, Senya's one of my, oh, don't give me that. Is it gonna do that to me? Come on. Oh no, I hate that when it does that. It gets stupid and asks me for a pin that doesn't exist, and I don't know why it does that to me. Where's my mouse? Well, it's in better. Hang on.
It's just circling through the different ways you can.
Yeah, I know, but it shouldn't. It was also telling me that I needed something that I don't have.
No, that's
So.
one of the ways you can.
Yeah, no, but not, this one doesn't have, there isn't a code for this one. It tells you look on the back of the TV. It becomes like a weird thing. Here it goes. Okay, needed to tap it. Yeah, this cute dog here on my screen is actually Senya's new dog. I had to share her picture. And cute. Senya's one of my junior cyber students. But he's sweet. They're talking about maybe naming him Big Mac. Yeah, he's a anyway.
Big old wolf.
He is a big old dog, yeah. So so nobody looked up for me what was in the space? So I found a couple of videos where people try to explain what's in the space. I don't think anybody did a great job. You can tell like Drew borrows my computer and puts ridiculous things on it. All kinds of stuff. Okay. What is in the space? Where's the guy who talks about gluons? Oh, this guy. So this guy had an answer, and this one had the best answer. So let's see.
One of the most amazing things about atoms is that they are mainly empty space. If an atom were as wide as your arm span, then the electrons would all be whizzing
Dude, why'd you stop?
About inside the volume enclosed by your fingertips. Meanwhile, the nucleus would be sitting in the center, and its diameter would be smaller than the width of a single human hair. So all of the atoms that make up you and me and all the seemingly solid things in the universe are mostly empty space. Now this is incredible, but what is even more mind-boggling is that empty space is not truly empty. I know because I've seen it. This is a simulation by Professor Derek Lineweber at the University of Adelaide. It was made using a supercomputer to crunch the calculations of quantum chromodynamics. Now that is the theory of fundamental particles called quarks, the building blocks of protons and neutrons, and how they interact with each other through gluons.
What you're looking at here is the energy density of the gluon field fluctuations. Where the little red spots come out, the energy density is very high, and it fades down through the colors. So at the lowest energy field fluctuations, I'm not rendering this animation so we can actually see into it.
And what we see is a bubbling soup of quantum field fluctuations that come and go incredibly quickly. The frame rate of this simulation is 1 million billion frames per second. Now that is truly high speed. The dimensions of this box are absolutely tiny. They are millionths of a billionth of a meter, roughly enough space to stick 2 protons. But there are no protons here. This is a simulation of the vacuum on its own. What we
You said
normally
vacuum
think
last
of
week,
as
Abby.
empty space.
Space is actually full of these quark and gluon field fluctuations. And on average, it is possible to annihilate a quark from empty space because it's not empty.
That just sounds like the most ridiculous idea that you're meant to have empty space and yet you can go and get rid of stuff from it.
That's right. So it isn't empty.
Now, it seems counterintuitive that the vacuum at its lowest energy state should contain all of this stuff. But in fact, to clear out the fluctuations and create a truly empty vacuum would require a lot of energy.
The empty vacuum actually costs an enormous amount of energy to create. And if you were able to create it, you discover that that is actually unstable, that any sort of perturbation would push that empty vacuum into something where the vacuum is actually full of fluctuations.
Well, this may not be as strange as it first appears. I mean, consider a permanent magnet. It has a magnetic field around it at low energy, at room temperature. And that's because the individual little magnetic moments of all the atoms inside are lined up. But if you were to heat it up, you would give thermal energy to all those particles, and at a certain point, called the Curie temperature, they would be so randomly aligned that there would no longer be an overall magnetic field. So it actually takes energy to get rid of the permanent magnetic field. And this is just like the quantum vacuum. And understanding how the quantum vacuum fluctuations work gives us a sense of what the fundamental particles do. Like,
I went full anime there for a second.
you're most likely to find a quark.
And it turns out the quark likes to sit on top of those lumps. Now those lumps come into and out of existence fairly quickly, and so we like to think of quarks as hopping from one lump over to the next lump as it appears, and then on to another one. I like to think of it as a hiker trying to cross a stream that's running around every now and then.
Yeah,
So
he's asking for it.
because the water's swirling around it, so you put your foot there and you look to the next spot, and you go quickly enough, you might not get your feet wet. So I think quarks are very much, well, we know quarks are very much doing the same thing.
So while it is true that you and I and all of the other atoms in the universe are mostly empty space, it is also true that empty space isn't truly empty. And in fact, it is these vacuum fluctuations which are essential for our existence.
If you're not subscribed to Derek's channel,
Derek.
I don't know what you're doing with your life.
Derek's got to get it worked out there. There you go.
Derek wants to subscribe.
So empty space isn't empty space, but it's full of all kinds of little teeny tiny things that we can't see. Super difficult to try and visualize. I like that they actually had an animation because that's one of the first I've seen like that. Usually people try to verbally explain it and it's so much fun.
Yeah,
All right. Did you? Yeah. All right. Any questions? I'm going to look up, like I said, some more math problems and some examples for you guys. Does anybody have any questions? Are you all good? Good. Oh, so I did hear one more joke, Michael. I saw one this morning where this lady said that she told someone she was distantly related to Marie Curie, who's a scientist that, you know, he just said the Curie principle. Anyway, and the person responded to her, no, it's pronounced Mariah Carey. Oh, yeah. All right. Well, I'm going to say goodbye to these folks here. And you tell everybody so long. Goodbye. See y'all later.
Awkwardly stare at camera.
Bye, guys. Yeah, sorry I missed that. I couldn't tell whether I was screen sharing or not at one point. I hope I came back for you guys, though, at some point. All right, good.